Hello students, and welcome to the lecture on modes of data transfer and serial communication. After this lecture, we will be able to learn the following objectives. Explain the introduction of modes of data transfer. Explain serial communication. Define asynchronous and synchronous communication. Explain programmed I/O. Define interrupt-initiated I/O and direct memory access.
Let's start with the introduction of modes of data transfer and serial communication. There are basically two formats of data transfer, parallel and serial. In parallel mode, data bits are transferred parallel over the communication lines, referred to as buses. Thus, all the bits of a byte are transferred simultaneously within the time frame allotted for the transmission. In serial data transfer, each data bit is sent sequentially over a single data bus line. In order to implement serial data transmission, the sender and receiver must divide the time frame allotted for the transmission of a byte into subintervals, during which each bit is sent and received. Serial communication is a popular means of transmitting data between a computer and a peripheral device, such as a programmable instrument or even another computer. Serial communication uses a transmitter to send data one bit at a time over a single communication line to a receiver. Let's now discuss the modes of data transfer. Modes of data transfer refer to the various modes by which the data residing in the memory is transferred to the CPU or back to the memory. The data originates from the input units. The originated data is then transferred to the memory for storage. This binary data received from any external device is in general stored in memory for later processing. So first one needs a transfer of data. Then for processing, the data residing in memory is read by the computer brain, the CPU, for carrying out various operations and transforming it to make it useful information. The CPU temporarily stores data just for the time being of executing the operation. Data to and from the peripherals are handled in one of the four possible modes: programmed input-output, interrupt-initiated input-output, interrupt-driven I/O, direct memory access, programmed input-output. Programmed input-output operations are the result of I/O instructions written in the computer program for transferring of data. Each data item transfer is initiated by an instruction written or specified in the program. Usually, the transfer is from the CPU register and peripherals like input and output devices. Other instructions are needed to transfer the data to and from the CPU and memory of the computer, not the peripherals. Once the process is initiated, the CPU is required to monitor the interface of the peripherals so that it can sense when the data can be transferred. It is up to the programmed instruction executed in the CPU to keep close tabs on the things that are carrying out in the interface and the I/O devices. Interrupt-initiated input-output. In the programmed I/O method, the CPU stays in a program loop until the I/O unit indicates for data transfer, which sometimes makes the CPU busy needlessly. This can be avoided by using an interrupt facility and special commands. Interrupt-driven I/O. Interrupt-driven I/O is defined as: in this method, the program issues the I/O command and then continues to execute until it is interrupted by the I/O hardware to signal the end of I/O operation. Here, the program enters a wait loop in which it repeatedly checks the device status. During this process, the processor is not performing any useful computation. Programmed I/O. In the programmed I/O method, the I/O device does not have direct access to memory. A transfer from an I/O device to memory requires the execution of several instructions by the CPU, including an input instruction to transfer the data from the device to the CPU, and a store instruction to transfer the data from the CPU to memory. Other instructions may be needed to verify that the data are available from the device and to count the numbers of words transferred. An example of data transfer from an I/O device through an interface into the CPU is when a device transfers bytes of data one at a time as they are available. When a byte of data is available, the device places it in the I/O bus and enables its data valid line. The interface accepts the byte into its data register and enables the data accepted line. The interface sets a bit in the status register that one will refer to as an F or flag bit. The device can now disable the data valid line, but it will not transfer another byte until the data accepted line is disabled by the interface. A program is written for the computer to check the flag in the status register to determine if a byte has been placed in the data register by the I/O device. This is done by reading the status register into a CPU register and checking the value of the flag bit. If the flag is equal to 1, the CPU reads the data from the data register. Interrupt initiated I/O and direct memory access. An alternative to the CPU constantly monitoring the flag is to let the interface inform the computer when it's ready to transfer data. This mode of transfer uses the interrupt facility. While the CPU is running a program, it does not check the flag. However, when the flag is set, the computer is momentarily interrupted from proceeding with the current program and is informed of the fact that the flag has been set. The CPU deviates from what it's doing to take care of the input or output transfer. After the transfer is completed, the computer returns to the program to continue what it was doing before the interrupt. The CPU responds to the interrupt signal by storing the return address from the program counter into a memory stack and then control branches to a service routine that processes the required I/O transfer. The way that the processor chooses the branch address of the service routine varies from one unit to another. In principle, there are two methods for accomplishing this. One is called vectored interrupt, and the other non-vectored interrupt. In a non-vectored interrupt, the branch address is assigned to a fixed location in memory. In a vectored interrupt, the source that interrupts supplies the branch information to the computer. This information is called the interrupt vector. In some computers, the interrupt vector is the first address of the I/O service routine. In other computers, the interrupt vector is an address that points to a location in memory where the beginning address of the I/O service routine is stored. The transfer of data between a fast storage device, such as magnetic disk and memory, is often limited by the speed of the CPU. Removing the CPU from the path and letting the peripheral device manage the memory buses directly would improve the speed of transfer. This transfer technique is called direct memory access, or DMA. During DMA transfer, the CPU is idle and has no control of the memory buses. A DMA controller takes over the buses to manage the transfer directly between the I/O device and memory. Programmed I/O, or PIO, refers to data transfers initiated by a CPU under driver software control to access registers or memory on a device. The CPU issues a command, then waits for I/O operations to be complete. As the CPU is faster than the I/O module, the problem with programmed I/O is that the CPU has to wait a long time for the I/O module of concern to be ready for either reception or transmission of data. The CPU, while waiting, must repeatedly check the status of the I/O module, and this process is known as polling. Interrupt. The CPU issues commands to the I/O module, then proceeds with its normal work until interrupted by an I/O device on completion of its work. For input, the device interrupts the CPU when new data has arrived and is ready to be retrieved by the system processor. The actual actions to perform depend on whether the device uses I/O ports or memory mapping. For output, the device delivers an interrupt, either when it is ready to accept new data or to acknowledge a successful data transfer. Memory mapped and DMA capable devices usually generate interrupts to tell the system they are done with the buffer.
When hardware devices on a computer produce events, we need some way of being able to handle those events within the operating system and deliver them to applications. And hardware devices are going to produce events at times and in patterns that we don't know about in advance. For example, we don't know which keys the user is going to press on the keyboard until the user actually presses those keys. If a cat walks across the keyboard, we're going to see a completely different pattern of key presses from which we would expect to see with a human user. Similarly, if we have incoming network packets, if we're running a server application or even just a workstation, and we have messages coming in from the network, we don't know the order and timing of those messages. We also don't know when the mouse is going to be moved, or when any other of a whole bunch of hardware events is going to occur. So how can we get the information generated by these events and make it available to our applications for use? Well, we have two options. First option is that we can poll each device. We can ask each device if it has any new information and retrieve that information. Or we can let the devices send a signal whenever they have information and have the operating system stop whatever it's doing and pick up that information. This is called an interrupt. The polling model of input involves the OS periodically polling each device for information. So every so often, the CPU is going to send a message to each hardware device in the system and say, hey, you have any data for me? And most of the time, the device is going to send back, no, don't really have any data for you. Other times, the device is going to send back some data. It's a really simple design, extremely simple to implement, but there are a number of problems with polling. First problem is that most of the time, when you're polling, the devices are not going to have any input data to deliver. Thus, polling is going to waste a whole lot of CPU time. The second issue that occurs is high latency. If I press a key on the keyboard, that keystroke is not going to get transmitted to the computer until the next time the CPU polls the keyboard to ask which keys have been pressed. If that time is set to be really short, I'll have good responsiveness, but the CPU is not going to get any useful work done. On the other hand, if we set that time length to be long enough for the CPU to get some work done, there's going to be a noticeable lag between the time I press a key and the time a character appears on the screen. Since the device must wait for a polling interval because it can translate input, we're going to have a high latency situation. And again, shortening that polling interval to try to reduce the latency simply wastes a whole lot of CPU time checking devices that have no input. So a better mechanism is to use a system called interrupts. And with interrupts, the hardware devices actually signal the operating system whenever events occur, or more precisely, they signal the CPU, and then it's up to the operating system to receive and handle that signal. What the operating system will do is it will preempt any running process. In other words, it will switch what we call context away from that running process to handle the event. Basically, it will move the program counter of the CPU to the code to handle that particular interrupt. This allows for a more responsive system than we could ever achieve through polling without having to waste a whole bunch of time asking idle devices for data. However, this does require a more complex implementation, and that implementation complexity begins at the hardware level. Specifically, within the CPU, we need to have a mechanism for checking and responding to interrupts. And this mechanism is implemented as part of the CPU's fetch-execute cycle. In the process of fetch-execute, the CPU is going to fetch an instruction from memory, increment the program counter, execute that instruction. But instead of simply going back to the next fetch, the CPU actually has to have additional hardware to check to see if an interrupt event is pending. If there is an interrupt pending, then the CPU has to be switched to kernel mode if it's running in user mode, so the privilege level needs to be escalated. Save the program counter by pushing it onto the stack, and load a program counter from a fixed memory location, and that fixed memory location is called the interrupt vector table, or IVT. So we load the program counter from the IVT, and then the CPU goes and executes that new instruction the next time the fetch execute cycle resumes. So the CPU actually moves from executing program code to executing code from the interrupt handler for the particular event. If no interrupt is pending at the end of an execute, then we simply go back to the next instruction, fetch. The interrupt vector table consists of an array of addresses of handlers. Each element in this array essentially gives the program counter location for the handler for a particular interrupt. Now, this handler is going to be in a subsystem of the kernel for a monolithic kernel, or this handler might invoke a call to an external server for a microkernel. In any case, however, the first handler by convention, element 0 of the array, is always the handler for the clock. Then handlers for different devices are in the array after the clock handler. So the interrupt vector is always mapped into the user part of memory. It's always available at all times so that the kernel can go and look up interrupt information whenever is necessary. An interrupt is processed by branching the program counter to the interrupt handler, executing the interrupt handling code, and then at the end of the interrupt handling code, there'll be an instruction to return from the interrupt. In the Intel assembly language, this is the IRET instruction, which loads the process program counter back from memory. It pops the stack to get the original program counter back, and goes ahead and changes the CPU back to user mode, so it removes the privilege escalation. The interrupt handling mechanism is thus able to handle events from hardware devices without having to poll each device individually to get data.
The basic operations of interrupt are: CPU issues read command. I/O module gets data from peripheral whilst CPU does other work. I/O module interrupts CPU. CPU requests data. I/O module transfers data. DMA is a method of transferring data from the computer's RAM to another part of the computer without processing it using the CPU. While most data that is input or output from the computer is processed by the CPU, some data does not require processing, or can be processed by another device. In these situations, DMA can save processing time and is a more efficient way to move data from the computer's memory to other devices. The CPU may be placed in an idle state in a variety of ways. One common method extensively used in microprocessors is to disable the buses through special control signals. Two control signals in the CPU facilitate the DMA transfer. The bus request, or BR input, is used by the DMA controller to request the CPU to relinquish control of the buses. When this input is active, the CPU terminates the execution of the current instruction and places the address bus, the data bus, and the read and write lines into a high impedance state that behaves like an open circuit, which means that the output is disconnected and does not have a logic significance. The CPU activates the bus grant, or BG, output to inform the external DMA that the buses are in the high impedance state. The DMA that originated the bus request can now take control of the buses to conduct memory transfers without processor intervention. When the DMA terminates the transfer, it disables the bus request line. The CPU disables the bus grant, takes control of the buses, and returns to its normal operation. Now we will learn about serial communication. Serial communication is the process of sending data one bit at a time. sequentially over a communication channel or computer bus. This is in contrast to parallel communication, where several bits are sent as a whole on a link with several parallel channels. Serial communication is used for all long-haul communication, and most computer networks, where the cost of cable and synchronization difficulties makes parallel communication impractical. Types of serial communication. Modem. A modem is a device that modulates an analog carrier signal to encode digital information and also demodulates such a carrier signal to decode the transmitted information. The goal is to produce a signal that can be transmitted easily and decoded to reproduce the original digital data. A modem can be used over any means of transmitting analog signals, from driven diodes to radio. A modem modulates outgoing digital signals from a computer or other digital. In recent years, the 2400 bits per second modem that could carry email has become obsolete. 14.4 kbps and 28.8 kbps modems were temporarily landing places on the way to the much higher bandwidth devices and carriers of tomorrow. From early 1998, most new personal computers came with 56 kbps modems. By comparison, using a digital integrated services digital network adapter instead of a conventional modem, the same telephone wire can now carry up to 128 kbps. With digital subscriber line or DSL systems now being deployed in a number of communities, bandwidth on twisted pair can be in the megabit range. Simplex. A simplex line carries information in one direction only. Simplex is a communications mode in which only one signal is transmitted, and it always goes in the same direction. Half duplex. A half duplex line is capable of transmitting in both directions, but in only one direction at a time. One modem acts as the transmitter and the other acts as the receiver. Turnaround time. The time required to switch a half duplex line from one direction to the other is called the turnaround time. Full duplex. A full duplex transmission system can send and receive data in both directions simultaneously. Synchronous transmission. Two units share a common clock frequency, and bits are transmitted continuously at that frequency. Information must be transmitted continuously to keep the clock frequencies in both units synchronized. Asynchronous transmission. Binary information is sent only when it's available, and the line remains idle when there is no information to be transmitted. Asynchronous and synchronous communication. Synchronous and asynchronous transmissions are two different methods of transmission synchronization. Synchronous transmissions are synchronized by an external clock, while asynchronous transmissions are synchronized by special signals along the transmission medium. Sending data encoded into the signal requires that the sender and receiver are both using the same encoding or decoding method and know where to look in the signal to find data. Asynchronous systems do not send separate information to indicate the encoding or clocking information. The receiver must decide the clocking of the signal on its own. This means that the receiver must decide where to look in the signal stream to find ones and zeros, and decide for itself where each individual bit stops and starts. This information is not in the data in the signal sent from the transmitting unit. Most communications between devices within computers and between computers and external devices are asynchronous. Asynchronous communications also include computer-based exchanges of messages for which the participants need not be available or online at the same time, but rather read and respond as their schedules permit. For example, email, discussion boards, and text messaging over cell phones. Advantages of asynchronous communication. Simple, does not require synchronization of both communication sides. Cheap, because asynchronous transmissions require less hardware. Setup is faster than other transmissions, so it's well suited for applications where messages are generated at irregular intervals. For example, data entry from the keyboard and the speed depends on different applications. Disadvantages of asynchronous communication. Large relative overhead. A high proportion of the transmitted bits are uniquely for control purposes and thus carry no useful information. Synchronous communications is the more efficient method of communication. Through synchronous communications, data is transmitted as frames of large data blocks rather than bulky individual bytes. One advantage of synchronous communication is that control information is easily inserted at the beginning and end of each block to ensure constant timing or synchronization. Another advantage of synchronous communication is that it is more efficient than asynchronous communication. For example, a 56 kbps dial-up synchronous line can carry 7,000 bytes per second, compared to a 56 kbps dial-up asynchronous line, which can only carry 5,600 bytes per second. When transmitting large amounts of information, this translates into a significant increase in speed and performance. Synchronous systems negotiate the communication parameters at the data link layer before communication begins. Basic synchronous systems will synchronize the signal clocks on both sides before transmission begins, reset their numeric counters, and take other steps. Advantages of synchronous communication. Lower overhead and thus greater throughput. Disadvantages of synchronous communication. Slightly more complex. Hardware is more expensive. Did you know asynchronous communication is used on RS-232 based serial devices, such as on an IBM-compatible computer's communication ports? Now in the end, let us summarize what we have learned in this lecture. Modes of data transfer refer to the various modes by which the data residing in the memory is transferred to the CPU or back to memory. Programmed I/O operations are the result of I/O instructions written in the computer program for transferring of data. In the programmed I/O method, the CPU stays in a program loop until the I/O unit indicates for data transfer, which sometimes makes the CPU busy needlessly. Programmed I/O, or PIO, refers to data transfers initiated by a CPU under driver software control to access registers or memory on a device. The transfer of data between a fast storage device, such as a magnetic disk and memory, is often limited by the speed of the CPU.